Hello, my name is Anthony, and this is my project on linear transformations. Now, the first question is, what are linear transformations? The basic definition is that a linear transformation is a function from one vector space to another that respects the underlying linear structure of each vector space. And another definition can be that a linear transformation is also known as a linear operator or map. The two vector spaces must have like the same underlying field. So down here is a basic example. We're given in the M times N matrix A, which can be thought as an operator or function. The matrix A operates on vector X, producing a new vector called A times X. And we can do A times X equals B. So solving A times X equals vector B amounts to finding all the vectors X that are transformed into vector B. So next we can go over where are they in our lives. So it's important to know that a linear transformation is not an application itself, but rather it is a model. So many of our real life processes are described or approximated by linear transformations. And some everyday examples that we have are conversion of temperature from Fahrenheit to Celsius to Kelvin, and cooking, calculations of tax, computer graphics. We can look in a mirror. All the buildings, they all have linear transformations, and pretty much everything we do has linear transformations if you look at it. So next we'll go through the different types of linear transformations. First off, there's the shear transformations. Then we have scaling transformation, basic reflection, projection, rotation, and etc. So the first one is the shear transformation. The definition of a shear transformation is a transformation in which all points along a line remain fixed while other points are shifted parallel to by a distance proportional to their perpendicular distance. So here we can see that turning a square into a parallelogram is a basic shear transformation, and it's important to know that the area remains the same. And this is just the shear transformation through the x direction. So if we do it mathematically, here is a example of shear transformation. Let's say we are given points A, B, and then the transformation for this would be x times y equals to x plus ay and y plus bx. So here we have the horizontal shear, the shear of points 1, 0. And to solve that, we can do points 4, 2 equals to 4 plus 2, and then 2 plus 0, which equals to 0.62, which is here up to the left. That's the shear along the x-axis. And then we have the shear along the y, which means that we're given that the shear is 0, 2, which is a vertical shear. Let's say we're given points 4, 2, which equals to 4 plus 0, and 2 plus 8, which equals to the points 4, 10, which is right here. The next form of linear transformation is called scaling transformation. And the basic idea of this is to just change the size of the object. And in the scaling process, you either expand or compress the dimensions of the object, so making it bigger or smaller. And here is a mathematical example of scaling a transformation. Say we're given vector 1, 1, and the scaling, and this is the scaling matrix right here, the basic scaling matrix, and we also have the identity matrix. Let's say that we want to scale it. We want to make this line be twice as huge, be twice as long. So we use the k equals 2, and then we plug it into the scaling matrix formula, and then we multiply it by the vector, which equals 2, 2. And then when we graph that, we can see it's twice as long as the original vector. The next form of transformation is called reflection. So the definition of a reflection matrix transformation is that flipping an object about a line without changing its shape or size. And right here, for an example, we can see that we want to find the reflection through the y equals x axis. And the basic transformation of that is this right here, this matrix. And we use the transformation matrix to multiply by the original vector, this triangle vector. And also this rotates it about 90 degrees, as we can see here, not 90 degrees, through the y equals x axis. And then we can see that the shape is still the same, the size is still the same, everything is the same except it just is reflected through the y equals x. The next form of a linear transformation is called a projection. And the basic definition is that a projection is a mapping of a set onto a subset. To simplify this definition, it's basically the shadow of what happens when you cast the line, and then it creates the shadow. Here's a mathematical example of the projection. So say we are given the vector v equals 1/2, 1 over 2, 1, 2, and then the projection, we want to find the projection onto the x-axis first. And right here we have the basic formula, and we just multiply it equals to vector 0, 2. And as we can see here, just an example, this is the original line, and then the projection onto the x-axis is the bottom line right here. And same thing for the y-axis, except the projection onto the y-axis formula is different with the 1 at the bottom right. So then we just do the same strategy, multiply by the original vector, and then we get the projection. Next form of linear transformation is rotations. And the basic idea of rotation is that it turns a figure about a fixed point called the center of rotation. An object and its rotation are the same shape and size, but the figures may be turned in different directions. Rotations may be clockwise or counterclockwise. As you can see with this example, it rotated about 90 degrees counterclockwise. And here's a mathematical example of a rotational transformation. Now again, if we're given vector v equals 1/2, the basic rotation matrix formula, is this right here. And let's say we want to rotate it 90 degrees, which equals to pi over 2. We plug that into the rotation matrix, and we're given our new matrix that we multiply by the original matrix to give the result of what happens when you want to rotate it 90 degrees. And here on the right, we see what happens. See here on the right, we have the visualization of it, rotating 90 degrees. Now that we know what they are, we must understand why they're useful and how they are used. For an example, cryptography. So the basic definition of cryptography is that it's the study of the techniques to protect sensitive communications by means of data encryption or decryption. And it's important to know that an invertible matrix can be used as a cipher to encrypt a message. So here's an example of how to encrypt a message. Say we're given the passcode JCS 2020. First of all, we need to assign each number and letter to a number variable and create it into a matrix. So we call it the passcode matrix B, and it's this huge matrix right here with all the variables assigned to the letters and numbers. And also we have to have an invertible matrix A. And this is just an example of an invertible matrix. And now to encrypt the message, the passcode, we need to multiply the invertible matrix times the passcode matrix in order to create the cipher matrix. And it's this big matrix right here. And now that we have that, the passcode is now encoded and it is now protected. Another form of linear transformations we can see is in game programming, such as images in computer games are points drawn together with lines that operate in space. The use of linear transformations is what allows interactions to occur in a computer. So once a linear transformation has been translated into a format that the computer recognizes, it can bring visuals to life. So for an example, such as creating the game Pac-Man. Pac-Man uses a bunch of linear transformations in order for the player to control the object. So for example, we have the matrix of vertices, and that allows us to create the objects that are to be controlled. And it's important to know that the homogeneous coordinates, so they allow the objects to translate 2D with a 3x3 matrix, so then it allows the objects to move around. And then after that, we can use matrix multiplication to set the objects to move, such as we have rotation, and that's the composite transformations. Uh, and that means that for it to rotate, we have to have the we have to have the object rotate from the center. And also there's scaling to make the objects bigger when it eats. And also, last but not least, translation, just basic movement of the object. And in conclusion, we know that linear transformations are important because they're in the essential study of linear algebra. This can be used for the purpose of scientific computing and modeling, with matrices and transformations as the central object of study. Thank you for listening.